Get started. Today's the big day, as you all know. We have to get this over with to get to the more important stuff. Some of you mentioned there's the German group here. The Germans of Princeton, they actually meet to watch the game. They meet in a place that's called the Yankee Doodle Tap Room. That is in the I think it's in the, what's that called? Nassau Inn Hotel. I think that's what it is, in case. So if you're interested, I thought maybe, to be fair to our American friends here, is not fair to go to the German place. So we're going to the Triumph. Triumph is a place here on Nassau Street. Is on the right if you go from here. Okay, so that's where I watched 2 years ago. When I was here teaching that same course, I watched Germany being kicked out of the European Championship by Italy. Any Italians here? That was a tough game. I came there when it was 2-0 already. That's why I want to stop early today, because if I had been there early enough, it would have been different. You guys should tell me what you think about this red card in the last game. That was not a red card, was it? Okay, good. Let's try to focus now. So we talked about turbulence yesterday, and we introduced turbulence as a random process that needs a statistical description. You cannot predict each single little eddy. It's impossible. And so we said we need a statistical description. We introduced certain ways of defining a mean, time average, an ensemble average. We used this Favre average. Doesn't matter. These are just operators that we can apply to a random field, or that we can apply to the equations describing the random field. And then we talked of certain simplifications that we make in turbulence, and we derived the mean flow equations. So the equations that describe the mean velocities, the mean as defined here in the beginning. And then when we derived this equation, there was one quantity that was unclosed, a tensor actually, that we don't know, and we need to model somehow. So that was the Reynolds stress tensor. And then we said maybe if we derive an equation for that, maybe that helps us. But we saw that doesn't help us, because in that equation then you have many other terms that are unclosed. So it just makes the problem worse in a sense. But then we said, okay, one of the really, really important quantities to describe turbulence is the turbulent kinetic energy. That's the most important one. If you think of turbulence as eddies, take an eddy. Then an eddy can be described by a velocity, kind of, let's say, in this picture, a rotation velocity or whatever. We call it then a velocity fluctuation that's imposed on the mean flow, and a length, okay? If you have these two, everything's defined. Then also you get a rotation time. You can get this from these two quantities and so on. So the first one is the kinetic energy, that is the velocity squared. And so we said from this Reynolds stress equation, we can contract this tensors, ui, uj, we can contract the tensor, and then we get an equation for this k. And we talked about the different terms, and we said this here is nothing else than turbulent transport term. It's unclosed because it has now a triple correlation, where the Reynolds stress tensor was just this correlation here. But you see, this still has the Reynolds stress tensor here. It has this triple. So this is just a turbulent transport term. This is production of turbulence, and this is dissipation of turbulence. And so we talked a little bit about where these come from. We said production is the turbulence draws the energy from the mean flow somehow, the kinetic energy from the mean flow, and then we said at the very, very smallest scales where the gradients are highest, that's where the dissipation then takes out turbulence fluctuation, or takes out the turbulent kinetic energy. Okay, so this is not solved. We want to talk about turbulence models now. The turbulence, the model typically I mean, there are different models. The most used model is this one here, the gradient transport model. That's a model that is very intuitive and is often used for terms like this. We know that this is a transport, a turbulent transport. It has mathematically, we said last time, it has the exact same form mathematically as the molecular transport. So think of molecular transport. What's molecular transport? You have a velocity, it goes this way, but each single molecule, it goes wild in all directions, okay? And that causes a transport in the mean. That causes a diffusion type process, okay? So turbulence is nothing else. You have the mean flow, let's say, it goes this way, but turbulent eddies, they go, in all directions. So because this has mathematically also the same form, we could say for the viscous stress tensor, we have a very good model. We know it depends on, it's proportional to a transport coefficient, which is a material property, times the strain rate tensor, okay? And so here we do the exact same thing. We say, okay, let's just say this has the same form, so we use the same model. So this now is proportional to a transport coefficient times the strain rate tensor. And this here comes just to make the properties of this thing correct. Let's not worry about this for now. So now, because turbulence is not is not in the material, this new T, what is the kinematic viscosity for the molecular transport? Here we have something else, so we call this the turbulent viscosity or the eddy viscosity, and that's not a material property. It depends somehow on the characteristics of the turbulence, okay? So this is how we model this term then, and you see here I had this unknown, and I model it, and now the problem is I have another unknown, okay? So does that help me at all? I have a model to model an unknown, and it gives me another unknown. Does that help me?
Maybe less dependent on your model.
Pardon?
Maybe the newest model is less sensitive.
No, that's it's very obvious if you look at the thing. Well, this could be highly nonlinear. Whatever happens here, this could be a function of this, and it could make it, hopefully, yeah, it could make it very nonlinear. This is just a scalar, right? This was a tensor, and so this has 6 unknowns, and now we have only 1 unknown. Okay, so in a sense, you could say this helped us already a little bit. And also, we put in some functional form here. So maybe that new T scalar is easier to model also. Also something that is a viscosity, this thing before it was UI, UJ, whatever that means. And now we have something we call the eddy viscosity. Maybe that's a little more intuitive. Okay, good. So there are different models for this. There is for example, so now the challenge is to model this thing. There's the so-called Prandtl's mixing length model. This is one of the first models. And then there is a TKE, is the turbulent kinetic energy based model. And then, what people use today is something like the K epsilon model. And the difference between these three really is in the level at which these are closed. So what we'll see, maybe if we look at these in a little more detail, there is this mixing length model. And what the mixing length model says is, so first of all, we could say, and that is important, it's not on the slides, but it's important. What are the units of kinematic viscosity? This says units of kinematic viscosity. What are units? Meters squared per second, okay? So if by dimensional arguments, if we want, this has to depend on the turbulence. We said the turbulence can be described by a velocity fluctuation and a length scale of the dominant eddies, okay? So if we want to build a viscosity from that, it would be just U prime, the velocity fluctuation, times a turbulent length scale, the length scale of the dynamically important eddies, okay? So this is how we want to model this. And now the question is just, how can we model these individual terms? Why do we do this? We say this depends on turbulence, and these are the quantities that describe turbulence. Dimensional analysis gives us this. Now we had one unknown, now we have two unknowns. Okay, it seems we're going the wrong way, but this is not a very intuitive quantity. If I would ask you, in a turbulent flow, how large is the turbulent viscosity? Can you estimate this? You would have to say maybe 1,000 meters squared per second. We have no feel for this, okay? If I ask you, what is the velocity fluctuation in a turbulent flow, jet flow? Take a turbulent jet. What is the velocity fluctuation? Let's say the jet exit velocity is 10 meters per second. Then you would say maybe 10, or maybe you say 1, or you say 20, whatever. But this is the right order of magnitude, okay? Same with a length scale. If I tell you the nozzle is like, 5 centimeters, you would say, well, then the length scale, it must be of that order somehow. It's not 1 kilometer, and it is not 10 to the minus 5 millimeters, okay? So these are very intuitive quantities, and they're easier to guess. And so here, this mixing length model, we just say, okay, take the LM, that's the L here, and then what's so Prandtl here, he was thinking, how can I model this? And it turns out you can just do this by series expansion. You just say I have a mean velocity gradient, and then if I go over a length L, which is the size of the eddy, then the mean velocity gives me a velocity difference, and that is probably my velocity fluctuation. So if you do that, then this is exactly what you get, okay? So this here is just the mean velocity field, or the gradients of the mean velocity field. So that's easy, but then you have this LM, and the LM needs to be guessed, okay? That's how the model was. So if you have a jet, you would have to say, LM, I think it's 5 centimeter, or whatever. Or maybe it's proportional to the distance from the nozzle, or something like that. But you have to guess that. So it's not a perfect model, okay? Length scale has to be guessed. So then the other thing is that this also says if there's no velocity gradient, there's no turbulence, okay? And very obvious, you could have a velocity gradient that generates turbulence, and then the turbulence is transported over here. Maybe the mean velocity gradient goes away, and you have turbulence where you have no velocity gradient. Or for example, in a jet, let's say on the center line, or pipe flow, on the center line is symmetry condition, and there's no velocity gradient. So this would mean in a pipe flow, you wouldn't have turbulence on the center line. So we need to come up with something else here for the velocity scale. And so the next model here is the turbulent kinetic energy model. That's already going quite close to modern models, where we say, okay, same thing again. L is still here. This is L. And then for the velocity scale, we say the velocity is just the square root of the kinetic energy. Okay? That's the velocity, the turbulent velocity fluctuation. And now where do we get K? K comes from this transport equation I showed you earlier. So let's see if we say anything about this. This is the K equation. And so here all we need to do now is we need to say, this we don't need to model anymore, right? Because this is closed. If I have a model for nu t, that gives you model for ui, uj. Okay, so this is within this model, this is closed already. This here we use a gradient transport assumption, and this here, there's a model for this also. So this needs to be closed, but that's how this model works. Okay, so here you solve an equation for kinetic energy, and you still have to guess this thing. So it's still a model. It's not complete in the sense that as a user, you don't need to have real good physical insight, okay? So now the models they use today are, let's say, K omega model or K epsilon model or things like that. And the K epsilon model, that's one of the most well-known, is the same thing. Here you say U prime times LT. U prime, that's again from the kinetic energy, is K to the 1/2. And then you say, now I need a second quantity. I want a second transport equation for a length scale. So you could solve an equation for a length scale, for example, but here, because epsilon, that's an important quantity, here people suggested to solve an equation for epsilon, okay? And then just by dimensional arguments, you have K, you have epsilon. Epsilon is the turbulent kinetic energy dissipation rate. You can find a form for this L. And it turns out L, K has units meter squared per second squared. Epsilon is a kinetic energy dissipation rate, so that has units kinetic energy per unit time. Okay, so there's meter squared per second cube. That's what it is. And so if you put these two together, LT, a length scale, is K to the 3/2 divided by epsilon. Okay, so I put these two together, this is what I have. And now I have two equations here. One is the K equation, one is the epsilon equation. And so you see we used for this what I call transport term, we just use a gradient transport assumption. There's the new T here again. And then we write, basically the way you do the epsilon equation is you just write the same equation. Transport, in a sense, is an empirical equation. These are the same terms here, advection, turbulent transport. And then the production and dissipation, also you use the same terms. You just make them dimensionally correct, so they fit this equation. That's what it is, okay? And then there are a lot of constants here, and these constants, they're given like this, let's say, for certain cases, and for other cases, for certain cases, these constants work well, and for other cases, they don't work, and you have to use the fit constant. So there's a lot of, with this K epsilon model, sometimes a lot of fitting here with this C epsilon 1 and C epsilon 2 constant. Okay, but that's a model one can use. This shows once more how these terms are modeled. This is the turbulent transport term here. Essentially, you just take this whole thing and say this turbulent transport, and you use a gradient transport assumption. Production term doesn't need to be modeled, as I said, because I can just plug in the model here for UJ, and it is closed. And this is all that was to be done. Okay, so this is just, yes?
For the Prandtl number, why do you have two Prandtl numbers?
Because these are not actual Prandtl numbers. This is not the Prandtl number. Yeah. This is a, you could say this is a Prandtl number for K. So the Prandtl number refers to a scalar. K is a scalar. And so this is just a Prandtl number that refers to K. And this here is a Prandtl number that refers to epsilon. But again, these are basically, they're fitting constants. Because really, this is, you could say, this is a scalar equation, so you would have to have a diffusivity here. But we use the exact same transport coefficient as for the momentum equation. Yeah. And then if you would do the same thing for the viscous term, then you would put a Prandtl number there. And so here also we call this a Prandtl number or a Schmidt number or whatever you want to call it. And then, these are just fit constants. Then they don't refer to molecular properties like an actual Prandtl number.
Yeah. And do you have a reference for this number? Because you say 1 and 1.3.
Yes, look in any turbulence book. You think they're different usually, or?
Because I used one in a reviewer told me that it was too high. So.
What, this is too high?
It's what he told me, but.
That's the point. These are, in a sense, these are fit constants. Yeah. These values here, you can actually determine them by writing these equations. If you write this model for isotropic turbulence, you can get the decay rate of isotropic turbulence as function of this C epsilon 2 parameter. Okay? And so if you know the decay rate from the experiment, you can just get C epsilon 2. And then C epsilon 1, you can, in a similar way, you can get for homogeneous turbulence. But these values that you get for these ideal cases, they don't work in real life. So the thing about the K-epsilon model is, in a sense, it's an empirical model. And for each different case, basically, you have to refit these values. But it's not as bad as it sounds, because if you compute a turbulent jet, planar jet, let's say, then we know these work. If you compute a round jet, we know they don't work. They don't work for a round jet. You get the wrong spreading rate. But people know values for this that also work for a round jet, and so on. So it's an empirical model, and one has to. So if you have a better set of coefficients, use your better set of coefficients for your case. Okay. Okay. So if you say it's too high or too low, that refers to your case, not for the general world. Okay, so good. So we have models now, but we want to look a little more in the turbulence physics, because that becomes important later on. I just want to show you how analysis is done in turbulence. In turbulence, we talk about these eddies and so on. And the question is, how do you... So we said we have an eddy has a velocity fluctuation. That's the turbulent kinetic energy. We have an equation for that. But the length scale, we don't have a real way of defining this for now. And so what people do in turbulence theory is they very often they look at these 2-point correlations. And the idea of this is that you take the velocity, you measure the velocity at this point and the velocity at a different point. Okay? And then you do this many, many times, and you look at if they correlate. If they correlate, that would mean they are part of the same eddy. You have velocity here, and I measure velocity way over here, and I have my turbulent eddies, they're much smaller than this distance, then most likely these are totally uncorrelated. Okay? So you get, when these points are very, very close together, they must be perfectly correlated, and when they're far apart, they're not correlated. And how fast this correlation drops tells me something about the size of the eddies and so on. And so this is the 2-point correlation here. The 2-point correlation is a very, very complex function, because you see I can correlate the u velocities, but I can also correlate the u and the v velocity. I can correlate the v velocity here with the u velocity over there. So it's a tensor. And then this correlation function is a function of space. I can evaluate this everywhere in my first point can be anywhere in space, and my second point can also be anywhere in space. Okay, so is a function in 6 dimensions. It's a function of time, and it's a 3x3 tensor. So it's relatively complicated. You can't measure this thing. I mean, it's impossible. Okay, so but anyways, for theory, you can use it. You can normalize this. If you normalize this here with so this here is just the u squared, that is just the correlation function for r goes to 0. Then it's just u squared at this point. So this means at r equal to 0, this has to be 1. Now this f function here, the correlation function. And then, as I said, for r goes to infinity, the correlation should go to 0. And then, how fast it goes to 0, that tells me something about the correlation. So we define our length scale, and also with this, we say the integral of this correlation function, that gives me the length scale of the large turbulent eddies. We call this, therefore, this length scale, we call it typically the integral length scale, because it comes from this integral. So integral length scale just means that's the length scale of the large motions of the turbulence. So interesting is that this is a function of r now, is a function of the distance of these 2 points, okay? And if you do a Fourier transform of this, then you get the energy function, which is a function now of the wave number, okay? And that's because you see, this basically has units, this here, or this r basically has units u squared, that units of an energy. This energy function, if you take this Fourier transform, that is basically energy as function of the wave number And the wave number is just the inverse of the length scale. So this energy spectrum function, it shows you the energy you have at a given eddy size, okay? So this is how it typically looks like, and what you see is that you have on a logarithmic scale or double logarithmic scale, and what you see is you have a lot of energy on the large scales. So small wave number would be large eddies. So this is small wave number. This is very high wave number. Small wave number, you have a lot of energy. Small wave number, you have almost no energy. But we said all the dissipation of the energy happens at these small scales. And we said the production happens at these large scales. So this means that this is how turbulence works. It's produced at the large scales and it's consumed or it's dissipated at the small scales. And so this means there must be some mechanism that converts large eddies into many smaller ones, these smaller ones into many even smaller ones, and so on. And so that's what we call the energy transfer here in this wave number space. And so you see you have this, and then this is what this vortex stretching mechanism I mentioned last time. It takes the energy of these large eddies and makes them smaller, smaller, and smaller. Okay. So there is in turbulence theory there are these Kolmogorov hypotheses, and that's something that really helps us understand the turbulence. And so the first thing that Kolmogorov said is when we look at these small eddies, if I look at the spectral content, I just look at all the eddies with very high wave number, then he said they must be all isotropic. You know, they don't know the direction anymore and so on, and there are reasons for that. And then he said the statistics of these eddies, they depend on only two parameters, and this is the dissipation, the turbulent kinetic energy dissipation rate, and kinematic viscosity. Okay, and if you assume that, so this comes from dimensional analysis, but really, I mean, the way he did it is he took the equations and he derived some equations, simplifies the equations, writes them for this, and then he sees it has these two parameters and nothing else. But if you say it depends only on these two parameters, then you can form a length scale from this. From these two parameters, and this length scale is the so-called Kolmogorov length scale. That is the length scale where now the advection process that makes the eddy smaller and smaller, and the viscous process that tries to damp out the turbulent fluctuations, where these are equal. And so this is the smallest length scale in turbulence. And you can also build a Kolmogorov time and a Kolmogorov velocity. So this is what describes these very smallest eddies. And you see, if you build a Reynolds number with these three, it's equal to 1, which basically means that now here the inertial and the viscous forces, they balance each other. Okay, so that's the first one. That's already very exciting. But then he came up with the second hypothesis here, which says now if I look at scales that are much smaller than the large scales, okay, then things don't depend on the large scales really anymore. And that was the first hypothesis. But then he said, what if I look at length scales that are much smaller than the large scales, but at the same time, they're much larger than the small scales, okay? Somewhere in between. If I'm much larger than the small scales, then it shouldn't depend on viscosity anymore, because the viscosity becomes only important at small scales, okay? So it says there must be a range, that's what we call the inertial subrange, that does not depend really on the geometry of the flow, the nozzle geometry or whatever, because it's so much smaller than the nozzle geometry, it doesn't know anything about it. And also, it doesn't know anything about viscosity. And so it must be independent also of viscosity. So this only depends on epsilon. And then epsilon is the energy transfer rate. So this is the rate of energy that's transferred from the large to the small scales. And then from this, you find the so-called Kolmogorov scaling turns out then that at any length scale, this is written here for the integral scale, but at any length scale, you can say epsilon is equal to, should write this down. So at any length scale, any wave number k, at any wave number k, then you can say the velocity fluctuation at that scale, cube, divided by this length scale is equal to epsilon. This is true for all scales. Okay, that's the so-called Kolmogorov scaling. This is very, very important for turbulence. And so this is basically written here for the large scales. And if you use this scaling, then you can find that the ratio of the Kolmogorov scale to the, so this is the smallest scale in turbulence, to the largest scale in turbulence, is proportional to Reynolds number to the minus 3/4. Okay, that's important sometimes when we do simulation. Okay, so that's just a little bit about turbulence theory. Then we talked about the Reynolds equation for the velocity. Here in combustion, we are often interested in scalars, so this would be the equation for mixture fraction. We can also here, we can do Favre averaging, and then we get these terms here, a molecular transport term and then a turbulent transport term. Molecular transport term is usually neglected in the Reynolds average context. And this here now is just modeled again with a gradient transport assumption. It's the same thing again. So here, gradient transport assumption for this, we have a dt. And the dt, if you assume a constant turbulent Schmidt number again, whatever the value is, choose whatever you want or whatever is good for you. People sometimes use 0.7 for this. And we relate it back to the eddy viscosity. We have a model for that already. Okay, so this is the equation here. Then the other thing that's important, so for the velocity field, we had an equation for the mean and then an equation for the kinetic energy. And here we can do the same thing. We want to have an equation for the mean and then one for the scalar fluctuation, some equation that tells us something about the scalar fluctuation, and that is the so-called scalar variance. So the variance, the fluctuation, here is just the instantaneous minus the mean. So I can take the equation for the instantaneous minus the equation for the mean. That gives me an equation here for the velocity, for the scalar fluctuation. Okay. Now I multiply that by z prime prime, an average, and then you see I get an equation here for, so this would then be 1/2 z prime prime squared average. Okay, that's the z prime prime squared average. That's the scalar variance. So if you do that, then this is what you get. See, I said it's 1/2 multiplied by 2, and you see the 2, it ends up here somewhere. But then this equation here is now, again, is very similar to the kinetic energy equation in the sense that you have here the unsteady term and the convection term or the advection term, and then here we have a turbulent transport term. We just model this again with a gradient transport assumption, and then here we have a production term, and again that depends on this so-called, so this here is the term that is the equivalent to the Reynolds stress tensor. Now just for the scalar, we call it the scalar flux, the turbulent scalar flux. And so this here again is modeled here with a eddy viscosity type model or eddy diffusivity type model, gradient transport model. And then we have this term here, the dissipation rate, and the dissipation rate is how it's defined. So it's the gradient of the fluctuations squared mean. So that is something that if you look at where it's important, that's important again only at the very smallest scales. Okay. And what this does, it's the dissipation of variance. And so for combustion, this is very, very important because if you think about it, let's say you have a fuel stream here and you have an air stream, and initially they are unmixed. So this here is some spatial coordinate, whatever, and this here is mixture fraction, and this is 1. And so you see here, I have in this part you have only fuel, and this part I have only air. Okay? What does the turbulence do? The turbulence just by itself, the eddies, they take some part of this and put it over here, and they take some of this and put it over here, but they don't mix really. So the turbulence, first of all, it would give you something that then looks like this. maybe. And then, now I can't draw this anymore, but then you have smaller eddies which would break this up again. Let me just try it. And you will get things that look like this, but you have them on all scales. But it's all 0 and 1. There's nothing in between. Okay, the turbulence just moves stuff from here to there, makes the scale smaller, the gradients large, and so on. But so the original profile here, that has in this part and this part no variance. Okay. But once the turbulence starts mixing this, you create a lot of variance. There's a lot of fluctuation. You see the mean here, the mean is something like this, but at each point I have the maximum possible fluctuation. Okay, so this gives you a large variance. And then dissipation here, that's what dissipation or the viscosity now does, or the diffusivity now does. It will mix these on a molecular level so that ultimately, you know, everything is mixed on a molecular level, which means it takes out the variance. So taking out the variance means mixing fuel and oxygen on a molecular scale. And remember we said earlier, for example, if you assume infinitely fast chemistry, then in non-premix combustion, which is what this is supposed to be here, in non-premix combustion, everything in non-premix combustion, your things mix, burn only. No, let's say for infinitely fast chemistry, then the burning rate depends only on mixing, on molecular mixing. And you see this term now, that is responsible, that's the rate of molecular mixing, really. Okay, so for infinitely fast chemistry, that here would be something like your reaction rate. Okay, but for finite rate chemistry, this is still very important, but then the chemistry also is important. Okay, but this term for combustion is very, very important to get this right, because it really gives you an estimate already, or an upper bound for the reaction rate. Okay. Okay, so this is how we model this. For the K epsilon, for the momentum field, we said we solve an equation for this. You could do this also here, but what's done here very often is that you say, oh, I can define a time scale from this. This has units 1 over a second. Let's start here. This has units kinetic energy, and this has units kinetic energy per second. Okay, so this ratio is second. So now if I do the same thing, if I define a scalar timescale here in exactly the same way, the dissipation rate in the denominator and the variance in the numerator, I also get a 1 over second or a second here. And so we say the timescales, the assumption here is that we assume the timescales are equal, or they're proportional to each other, like here. So if we do that, then the dissipation rate is epsilon over k times the variance. Okay, so then this equation, if I use this, then the equation is closed. So that we assume the timescales are equal. Now we can do the same thing for the reactive scalars. Let's take the temperature here, chemical source term. This is the species equation, also chemical source term. You see the form of these is roughly the same if I neglect a few terms here for the temperature, which we do here just for illustration purposes. But then I can define a scalar here, reactive scalar, you know, could be either one of these, either the species or the temperature, okay? And then I have this equation, this is a source term, and I take the average, or I introduce here the Favre decomposition, take the average, and I get the same equation as before, just with the extra chemical source term. And I can make the same modeling assumptions, and again, the only thing that's different here is really this chemical source term. Now, the chemical source term is not so simple. It's very nonlinear. And we said if it's nonlinear, then you get these correlations. Like the Reynolds stress, we got this only because the advection term is nonlinear. And this here is not only as, I mean, the Reynolds stress is like Mickey Mouse. The advection term is like Mickey Mouse compared to the chemical source term. Right? The chemical source term is so nonlinear that you would expect something, you know, big to happen in this correlation term. I mean, given the fact that the Reynolds stress term already made a huge difference. Okay, so that's something to keep in mind, and we'll talk about this in one of the next lectures. What the error is we make when we model this in a naive way, and also how we can model this in a better way, maybe. Okay, at the end, I just want to say a few words about large eddy simulation. Large eddy simulation, so maybe first about direct numerical simulation. I used these terms already. Direct numerical simulation means nothing else than taking the governing equations, maybe the Navier-Stokes equations, plus the scalar equations, energy equation, and everything, without any modeling assumption, and just solving these equations. Now, without any modeling assumption is not actually true. If you just solve the momentum equation, you know, the momentum equation has the viscous stress term. That is a model already, but we just know this model is just perfect. I mean, the model we use for the viscous stress with kinematic viscosity or the dynamic viscosity, that's just a perfect model. And so we say these are the true equations that describe the true flow physics. And it turns out they do. I mean, this is really, really good. So when you add then the scalar equations, then you have a chemical source term. You have to have a chemical mechanism, reaction mechanism. You know, these are models. But so in a sense, you make some assumptions, but this is what we call, this is the true world. Okay? Given a chemical mechanism, this would be the truth. And so why do we talk about modeling at all if we could just solve these equations? And the fact is that you can solve these equations for true turbulent flow, everything, but you can solve them only for a very, very small volume because it's just so expensive to solve these, because in turbulence you have such a big range of different length scales. That's the real problem. So if we want to estimate what it takes to do this, then we said earlier, let's say I want to do a simulation for turbulence in a box, okay? And I know I have large eddies. They need to fit in the box, so the box needs to be maybe 3-4 times as large as the largest eddies, which would be the integral scale, okay? But then I know I have small eddies also, the up-down to the Kolmogorov scale, and I know I need to resolve these also, okay? So my box size, that's on the order of LT, and then the number of points I need in each direction to resolve also the Kolmogorov scale. That should then be an LT divided by eta. That gives me an estimate for the number of points I need to resolve this. So this is the number of points in each direction. We said L over eta, that's equal to Reynolds to the 3/4. That's what we got out of the Kolmogorov scaling a few slides ago. So that's the number of points I need in one direction. Now in 3D, we said turbulence is always 3D. This would be Reynolds to the 9/4. Okay, that's, so if you say, now you can estimate the jet Reynolds number, so this is the turbulence Reynolds number. Jet Reynolds number is typically 50 times the turbulence Reynolds number. If you have a jet with a jet Reynolds number of 15,000, then the number of points you need is like 375,000. That doesn't seem so much, but the point is that would be just for one integral scale. See, this is one little area here. If I want to compute this whole thing, you can imagine, is huge what I need. So, by the way, this picture is taken from the book of Steve Pope. It's called Turbulent Flows. Nice book on turbulence. So I teach my course at home. I teach turbulence course, which I do according to this book. And you see some of the material in this lecture is also from this book. I just want to acknowledge this. So that's DNS. DNS is very, very expensive, and it can only be done for certain cases. And we do DNS usually just for certain, a little bit idealized cases to see then if the models work for these cases, okay? So in large eddy simulation then, so what we did for Reynolds averaging, we said, okay, this is one realization of the flow, and why don't we take 1,000 realization of the flow or 10,000 realization of the flow, and we average these all together. Okay, that's one way to do it. And then there's no turbulence left in this. I mean, there's no turbulence dynamics left in this. You might still have unsteadiness, but that's not turbulence, okay? Because I just averaged out all the turbulence. Now, in large eddy simulation, what we do is, rather we say we can't resolve all the scales. And so we say let's apply a spatial filter. It's like a high-pass filter, where we filter out all the small-scale fluctuations. Okay, and we filter out so much that what's left over can be resolved. We can resolve this on a, on a mesh that we can afford. So if you do that, that spatial filtering, this is a video here. I'm not sure if this is running now. Yes. So this here is a time average of this. And you see now the averaging time window gets shorter and shorter, and you see how this becomes ultimately, the instantaneous flow. This actually, I'm not sure it's a good video, just looks nice, but because it should better do instead of time averaging, we don't do time averaging in LES. It should just show you the difference between a fully dynamic simulation and something that is time averaged. So this is an LES, but in the true DNS now, you would see the exact same thing, plus more fluctuations on the smaller scales. Let's see what else this thing does. Oh, maybe we should just move on. Anything else coming here? Oh, it just rotates a little bit. Okay, let's see if there's anything interesting. I can't remember what I think it's just the same. Okay, let's move on. So this is kind of the idea. This is what we do. Take an instantaneous velocity signal. Let's say the red line here, that would be, let's say take a jet, and then we take a measurement along a line of a velocity, and then this would be the velocity here. Let's say this red line. And then you see that the very small scales, I would need to have many, many grid points to resolve the red line, okay? But in LES, we say we apply a filter. So typically, you have a filter kernel, and you convolute the velocity field with this filter kernel to get a filtered velocity. And now, we have to be careful. I use the overbar as to denote a Reynolds average so far. Okay, here I use the overbar to denote the filtering. Okay, just keep that in mind. So this would be the black then would be the filtered field. So if you look at this in this energy spectrum function, we said we have, this is the energy of the different scales. These are the very small scales. And so here, this is all just filtered out, and what's left over is just this part. And this has a good advantage because this has two big advantages, actually three. Number one, first advantage, all the energy, this is a log scale, log scale. So this compared to this is huge, okay? And this here, as you see, all the energy basically is resolved. Only a very, very small part of the energy is filtered out, okay? So that the whole dynamics of the flow, maybe it's not so bad. Second advantage, this now needs to be modeled. You can't just take it out and not correct for it. So we need to introduce a correction for this. But the modeling of this term is a lot simpler than modeling the entire turbulence, because we said earlier the small scale turbulence is isotropic. Okay, it has the same statistics in all directions and so on. So isotropic turbulence is much easier to model than the full turbulence. That's second. And then the third is, and many of you might have heard about this, is that you can use, in this modeling, you can also use so-called dynamic models. We said earlier, you have these models, and you always have these constants, and you need to fit these constants somehow. In dynamic models, what you do is you also have constants. You have coefficients now. Coefficients. if you look at this, let's say you don't know what this is. Let's say you don't know this, okay? Because you need to model it, you don't solve it. But you solved all this. Now, you see, I get a lot of information about the spectral content of this. And you could now estimate, you know, if I would ask you, how does this look like? You would say, it probably just looks like this. I mean, you don't know where it goes down here, but you kind of know it goes like this. So you can use the spectral content that you compute on the large scales to estimate the constants that you use to model the small scales. Yes?
For the filter velocity, I see that you need the velocity field, but you don't have it.
The instantaneous velocity field. Is that what you mean?
Yeah.
Yes. So if you had an experiment, then you know this is how you would evaluate it. But just like when we defined the average, the Reynolds average, we defined the Reynolds average with an instantaneous velocity, right? It was the average of the instantaneous field. And then we said we have the equation for the instantaneous field, and then we apply this operator to that equation. Here's the same thing. We don't have this, but we have an equation that describes this. The instantaneous momentum equation, that describes the dynamics of this. And we take the equation and we apply this filtering operator to that equation, and that gives us an equation then for this filtered field. Okay, this is very similar to what we did before. So these filters, there are different filters you can use. Box filter, the spectral filter. So this would be basically a box filter. You average over a box. And then the spectral filter is you also average over a box, but in spectral space. This is interesting that if you take the box filter, so this is space, and this is how this filter looks like. So it's just a box, right? It's 0 everywhere, and it's 1 within the box. And if I now take an average over the entire field, it will just give me the average of this within this box. So if I take the Fourier transform of this, you see, here I take the Fourier transform of this, you see in wave number space now it's not local. This averages over all wave numbers. And vice versa, if I take a box filter in wave number space, it will be non-local in physical space. That's just an interesting fact. If you take a Gaussian, you can also take a Gaussian function as a filter. Turns out that's compact in both physical and wave number space. So that's might be a good choice. Okay, so as I said, we can take the instantaneous equation, apply the filtering operator. This is what I get. Again, I get you know, something interesting here from the advection term. I write it like this term. I write it like this. I write you know, this is what we call the subfilter Reynolds stress plus this, and then this is how I can write the equation. And you see, this is now very similar. This in the form of this is very similar to the Reynolds equation. It just has different meaning. This here now is a Reynolds stress, but is a subfilter Reynolds stress. That's the Reynolds stress that results just from the scales that are filtered out, not from the scales that are still in the game. Okay, so now I can think of a model for this. This is how it looks like, and this nu r here now, this is much smaller than the eddy viscosity in the Reynolds averaged model. Okay, because it accounts for only a little part of the turbulence. Okay, so what's interesting now, earlier we had these 3 different models. We said there's the Prandtl's mixing length model, and this was the simplest of all models. And then there was the K equation model and so on, and the K epsilon model and other models of that sort. Now, what should we do here? I mean, we said it's a similar modeling problem. And what people use here is the so-called Smagorinsky model. Turns out that is the same as the Prandtl's mixing length model. So that's the simplest of all models. Okay, just give it a different name, and it sounds fancy. So now there's a reason why you would do that. What was the problem with the mixing length model is that you, as a user, you have to prescribe the length scale of the turbulence. But here, because you say, see here, the filter has a length scale. So here you see the filter has this length scale delta, And that is prescribed anyways. And with delta, I filter all this out. And so we know what the relevant length scale is for the subfilter contribution to the turbulence, and because it's exactly the filter size, okay? So because we know what the length scale is, we can use the mixing length model is given here, so is U prime times L, and the L now that's the filter size, and the U prime, we take it again here from this rate of strain, or from the rate of strain. And so this is what it is then. This here is the Smagorinsky length scale, and as I said, Smagorinsky length scale, that's just a constant times the filter width, the filter that I applied to filter the velocity field. Okay, so that gives me more. Was there a question? Yes.
How do you select the filter size?
Yes, how do you select the filter size? That's a very good question, because it is interesting that this model leaves that open to you. Okay. The LES leaves it open to the user to select the filter size, and I can tell you, typically it's selected incorrectly. The filter size, what we typically do is implicit filtering in LES. Implicit filtering means I take the mesh, my computational mesh, I take that as the filter size, or I take the filter size as my computational mesh size. Okay, that means your computational mesh that changes in certain ways. But when you put together your computational mesh, you usually don't think, how should I do this so that my filter size is correct also? Generally, you can say your filter size depends on your wallet. How much money you have in your pocket depends, that gives you the filter size. If you have a lot of money, make the filter very small. You will get a very accurate solution. Make it so small that you do DNS. I mean, the nice thing is you make the filter smaller and smaller, you resolve more and more. And you go towards DNS in a sense. Okay? But on the other hand, if you don't have much money, you have to make coarser. But it's very obvious that you need to resolve the energy containing part. Now, if you look at this here, again, most of the energy is at these large scales. So take the integral scale divided by 10 or so. That is the minimum you should do. Now, you would have to estimate the integral scale at each point. And I'll talk about this a little more later, how to choose this. But you have to think about it. When you make your mesh, you have to think about, is this good also for my filter? Right, there's one more thing that is interesting. In combustion, we said, combustion takes place when fuel and oxidizer are mixed on a molecular level. But that is only because of the dissipation. And we said the dissipation takes all place here at these very small scales, which means you can resolve more and more and more. You don't get to the point where you resolve the combustion process. That is why LES, is magic for cold flows, for, let's say constant density flows. But for combustion, it doesn't do the same magic I said earlier. The nice thing is the kinetic energy is resolved. Combustion is not resolved at all. It's never resolved. Okay? Very small part of combustion are resolved. Why is it still good, though? I mean, what we see is that LES is very, very good for combustion processes. Why is that? Because combustion, it happens all at these small scales, which always have to be modeled. But combustion depends very, very strongly on mixing, scalar mixing. And scalar mixing depends very much on what happens on the large scales, okay? And if you predict the large scales much more accurately, then you will also predict the mixing process much more accurately, and by that, the combustion process. So that's a very simple reason why we see that LES is always much, much better, more accurate than Reynolds averaging.
You didn't talk about the backward effect, where the energy will go from the small scale to the...
Yes, I didn't talk about many things, and that's one of them. This is a turbulence course in 1 hour. Usually a turbulence course should be 3 years or so. So there are many things I can talk about. So we said earlier, in the mean, okay, we talk about the mean. In the mean, the energy always goes from large to small. But locally, if you would look at the energy fluxes here, they always go in both directions. I mean, you always have energy going this way and that way, and that's called the backscatter. A lot of discussion about backscatter and what exactly backscatter is. So I think this goes too far for this. Yes?
Can you use non-uniform mesh when you're using ABS? Like how bad the simulation is if you use non-uniform?
No, we use non-uniform mesh. Yeah. No, I think well, non-uniform mesh always affects any discretization. So if you think of let me step back. The reason for the question, does non-uniform mesh, is that good for LES? When you think of Reynolds averaging, we said the Reynolds averaging operator, it commutes with the derivative. Okay? So the derivative doesn't matter. Here, the filter operator, it does not commute with the derivative because it's a function of space. The filter itself is a function of space. So it doesn't commute with the derivative. However, so you would get extra terms, but we neglect these terms typically. Okay, we say they're small. And especially now when you have a non-uniform mesh, this would become an issue. But, and now I come back to let's say you take a finite difference discretization. Then let's say you have a second order discretization. Then the second order discretization is if you have a uniform mesh. If your mesh is very strongly non-uniform, you go back to first order. Okay? So that's always the same. If you have very strong, from cell to cell, you have very strongly inhomogeneous mesh size, then things get worse. That's the same for LES, that's the same for the discretization. So if it's non-uniform, you make it not so strongly non-uniform. The changes from cell to cell should always be, let's say, less than 10% or 10% or something, and not stronger. So now this brings a problem to methods where you divide cells in two. Local mesh refinement, where you take a cell and divide it in two. If you need to do that, then you know either you do something special to take care of the numerics, or you just accept that you go back to first order. Maybe if you do this just locally in one point, just in one interface, maybe it's not so bad. But I think for LES also it's an issue, but even for discretization is an issue. So if you have thought very hard about the discretization, that's probably you did most of what you need to do. Okay, let's see. Maybe just flip through this and see if I'm at the end here, then we can take a break, right? So these were just a few words about generally how LES works. I didn't say much about dynamic models, but dynamic models would just be a way to compute this coefficient here if it's not prescribed, as a constant. And well, maybe we just stop here, take a break, and then we'll meet back in 10 minutes from now, 1 minute before 10.